let's use this diol. I remember in previous class, they always called this the headphones reagent, which it took me a little while to see, but now I see it. So, oh yeah, you have to use the headphones. Okay. So then we'll use this diol in the presence of acid, and it's like we get this cyclic acetal. So I encourage you to be a step ahead of me as we draw this. And so we have our ketone in the presence of our generic acid. We'll just put it hydronium. And so the first step is we're going to protonate this. All steps, again, are reversible. I'm trying to make it a little bit bigger. Now let's have our diol attack. Just have this OH point out over here. Keep track of things. So this dangling over here. And this oxygen now has a positive formal charge. So this mechanism, I think, is one that one probably would want to know for the exam. Again, not to memorize, but to be, I'll just say, how about be familiar enough with it that one could draw it. Sounds pretty close to the memorizing. Let's take the proton off. And as a subtle hint, I would also encourage people to think about this in reverse. We generated our hydronium. Let's go ahead and protonate. We have our good leaving group. I'm going to swing this one around in a second, I think. So now we have our good leaving group. It's not an SN2 reaction, but we have these lone pairs of electrons on this oxygen, which can kick out water. Reforming our carbonyl group. We have here. Now we have this hydroxyl group attached that's nearby. Disconnect as a nucleophile. Attack the carbon, move the electrons up onto the oxygen. So that's going to form a new bond now between this carbon, carbonyl carbon, and the oxygen. Which is what forms our cyclic structure. And then all we need to do is to take that proton off. And this will form our cyclic acetal. So same mechanism, but in this case it's a cyclic acetal. And I also bring this one up, well, for two reasons. One is because this is a very common acetal that's used in organic chemistry. We'll see it's used as a protecting group. And then also we'll see more examples where we go from something that is acyclic or not cyclic, like the example that we had above, pointing up above there, I guess, to a cyclic structure. And the cyclic ones are oftentimes harder to kind of sort out and count the carbons. But mechanistically, it's the same thing. So even though the structure looks more complicated, the concept behind the formation of it is actually the same. So then these acetals is we're setting up the stage for carbohydrate chemistry, for the sugar chemistry, because it's acetal chemistry.
Can you go back up for a second?
Oh, sure.
I just want to make sure I have it all.
Mm-hmm. Probably should have written it more clearly, but
Okay.
yeah, got it? All right, yeah.
Got it,
So that's excellent. You're welcome. So it's the same idea as the previous one. So we're going to protonate the carbonyl, a nucleophile attacks, take a proton off, put a proton on, kick out our good leaving group with water. Now we formed our carbonyl group, second nucleophilic attack, deprotonate, and we have our final product. Now, I have this one here yet. So all of these reactions are reversible. You can actually control them. The direction of the reaction, say by the amount of water that you have in the reaction. Go back to Le Chatelier's principle. And this is useful because we can use this acetal as a protecting group. So let's say you wanted to make this compound on the right, so for synthesis. So we have a compound that has a benzene ring, carbonyl group, a ketone, and a carboxylic acid. And we want to synthesize that starting with this compound on the left. Now, we could turn this aryl bromide to a Grignard reagent and react it with, say, carbon dioxide. So maybe we could have carbon dioxide and this Grignard reagent. And this should allow us then to have this attack carbon dioxide generate our final carboxylic acid that we want. However, this is going to be a problem because this compound will react with another equivalent of it. And what I mean is that imagine you have some of this around as well, or the Grignard reagent. This is just going to go and react with that ketone. So this was an incompatibility like what we saw with the alcohols in the Grignard reagent. Here we have a carbonyl group already on the compound, but we don't want that one to react. So what we need to do is we need a protecting group. So maybe this would be the approach, but that's not going to work. So we need a protecting group. So before with an alcohol, we turn that into a sialoether. Here the acetal works as a good protecting group. So what we can do, so we redraw this starting material. Let's just treat this with our cyclic acetal as the one that's commonly used, or we're going to form. These are reversible, but we'll go in the forward direction. So we're going to treat this with a little bit of acid, like sulfuric acid or H3O plus as we had, and we'll heat it up a bit. That's what the triangle means. That's going to form our cyclic acetal. So this is all the same. But this is now our acetal. So now, just like we saw with the sialoethers, the ether is less reactive. Same thing with the acetal here. So now what we can do is carry out, let's put all the steps together. We can take magnesium and ether. We're going to turn this compound into our Grignard reagent. We're going to react this with carbon dioxide. And then we're going to protonate at the end. So all of these steps together are going to introduce our carbon dioxide into a carboxylic acid. And we still have our acetal over here. Now, we want this compound on the top here that has the ketone, not the acetal. And that's no problem because all of these reactions are reversible. Here with the acetal, so all we have to do is add in a little bit of acid and some heat again. And we're going to remove that acetal and reform our ketone. Oops. So this is a good protecting group. And it has the 3 steps like what we saw before. So here we're going to protect. This is the reaction of interest, I think we called it last time. And then over here, we're going to deep protect. So that adds another tool for our toolbox, is that we have now protecting groups for alcohols with the silyl groups. Now we have a protecting group for a carbonyl group, such as an aldehyde or a ketone most commonly used, and that's the acetal. Doesn't have to be the cyclic acetal, but that's one that's commonly used. I'll scroll up to the page before, or is this? I'll keep going. No. I can go to the previous page, or? Got it? Okay. And Kyle asked the last catalyst. Is that, maybe are you referring to this scribbling over here? Oh, it's not, yeah, Jonium. Oh, man. That looks really bad. Let's try it again. H3O plus. And heat. Okay. So these acetals are actually also good protecting groups for alcohols.